Good morning and welcome back to Dr. Logic Awkwardly Does Logic. So you'll remember from last time, we're in the midst of this great big circle that has frame properties, different properties that our accessibility relation might have, and modal principles, various factors that we might want to ensure are true in our particular modal interpretation, whether it's epistemic or temporal or logical, and something that kind of brings the two together. Today, we're going to talk about one of these bringing them together steps. And in particular, I'm going to give an example of a correspondence result, which is where we take frame property on the one hand, validity of a modal principle on the other hand, and we put them together so that we have, wherever we have one, we have the other, and vice versa. So I'll start with a simple example. And this is one of the one of the modal principles that most people just assume is baked into our conception of modality. And that is the principle that necessity implies truth. Now, for the vast majority of ways we can interpret modality, what type of necessity we're talking about, this is a good principle. So we definitely do want to be able to include it. However, it's not something that's going to be across the board accessible, or it's not something that we want in every modal system. For instance, as I think I said last time, if we interpret the necessity as doxastic necessity, so talking about belief, this formula would then be if P is believed, then P is true. So that's a bad modal principle. We do not want necessity to imply truth as a general rule. We want it to do this only in particular modal cases. So what cases are those? The correspondence result that we're going to prove is that these are the cases. So when we have this modal principle being valid, these are going to be the cases where every world is accessible to itself. So when we are looking at what are the relevant possibilities, in a sense, the actual world is always going to be relevant. So every world is relevant to itself. So with that as way of background, the lemma that we are going to prove is this. We will prove that the formula necessary P implies P is valid on a frame if and only if that frame is reflexive, i.e., for every x, x sees x. So this is a biconditional. This means that we have two directions that we need to prove, and we will start with the right to left direction. So if a frame is reflexive, then necessarily P implies P will be valid on the frame. So starting with that direction. Because each individual direction is a hypothetical statement, we assume the antecedent and try to prove the consequent. So we will start off by assuming that we have a reflexive frame. So F is reflexive. Every world on that frame sees itself. Now we want to prove that a particular formula is valid on that frame. Let's suppose it isn't and try to come up with a counter model. So suppose that, in fact, necessary P implies P is not valid on this frame. Then what we know is that there is some model M on that frame and a world in that model such that the formula is false at that world. Now, if a conditional is false, this means that the antecedent is true at the world, so necessarily P is true, and the consequent is false, which is, we can also say that this means that not P is true. Now, F is reflexive, so W sees itself. Since P is necessary at W, by the definition of truth, it follows that P must be true at W. So by the definition of truth, we have that P is true. But this and this are contradictions. So our attempt to make the formula false, given that the entire frame is reflexive, we ran into trouble. So there you have it. The other direction is the one that's a bit more complicated. So strictly speaking, what it says is that if the formula is valid, then the frame is reflexive. But what we're going to prove is actually the contrapositive of that. We will show that if you have a frame that is not reflexive, then the formula is not valid on the frame, i.e., you can construct a model that makes the formula false at some world. So this is proved contrapositively. And we start by assuming that F is not reflexive. This means that there is some world in W, some world W in the frame, such that it's not the case that W sees itself. Now, all of the other worlds in the frame might be. It could be that this is like the only non-reflexive point in the frame. It could also be that it's the only point in the frame. Maybe there's nothing else. Maybe W sees other things. Maybe it's a dead end. We don't know any of that. All that we know is that in this frame, there's one world that doesn't see itself. With that information, we can, however, define a model. So remember that a model is just the addition of a valuation to a frame. That means that we need to say what values the atoms have at each of the worlds. So we define a model M on this frame F as follows. Now we want it to be the case that necessary P implies P is false at W. So in order to have that, it needs to be the case that the value of P at W is false because it's the consequent of the conditional. But we also need to ensure that the antecedent is true. The antecedent is necessary P. So we have first this, that P is false at W, but then we also have a general claim that the value of P at a world V is true. And this is the case for every world V that W sees. Now, it might not see anything, but then it's a dead end and it trivially makes necessary P true. It might see an infinity of them, but if P is true at all of them, then by the definition of truth, necessary P will be true at W. And because we know that W does not see itself, we know that conditions 1 and 2 do not contradict each other. And then we have to say something about all of the other worlds and all of the other atoms in order to make this a complete model. But that's easy. In this step, we just say everything else is arbitrary. It doesn't matter what value you assign to Q or to R, or what value P gets at worlds other than world W or worlds related to W. It's entirely irrelevant. So by 2, we have that necessary P is true at W. Sorry, by 1, we have that P is not true at W. So it's not the case that necessary P implies P. So now what we have is we have one world in one model on this frame that makes the formula false. But that means that it cannot be valid on the frame because that requires it to be true at every world in every model. So from that, we can say that it is not valid And now you've seen that we've assumed that the frame is not reflexive and shown that the formula is not valid. So taking the contrapositive again, if the formula is valid, then it has to be the case that the frame is reflexive. So there you have it. It's our first correspondence result. I will give you, probably in the next video, a couple other examples for you to try on your own to go through the process. It's going to be exactly the same. One direction you prove straightforward, the other one you prove in a contrapositive fashion. And I'll give you one more example so that you can see like what are the bits that were specific to this proof and what are the bits that are more general. The important thing is that when you are defining your model, it has to be a model that works for any frame that fails to meet the condition. Sometimes people get stuck and they say, here's one model that works for one particular frame, but that's not enough. You need the model to be able to work whatever frame you have. And so you need to think about kind of all of the bits of the structure of the frame that we don't know about, given that all that we know is that it is, in this case, non-reflexive. So I'll give you more examples because we're at this point, basically all logic is here's some definitions and here's how to apply them. Here's some results. Here's some examples. But I hope that you find the examples useful. If not, skip over them. Soon we will be coming to the point where we can bring all of these things together and start defining modal systems. So I hope to see you again soon. Take care. Cheers.